right, here we go. Word problem. We want to plant a rectangular garden along one side of a house, and we want to put a fence on the other three sides of this garden. And so what we want to do is we want to find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. All right, so it's word problem time. So kind of one of the key words here, or key phrases that kind of clues us in that it's an optimization problem, is right here, largest. We want to find the dimensions of the largest garden. So whenever we're trying to find an IST, largest, smallest, maximize, minimize, it's kind of a clue that we're dealing with an optimization problem. Now, we've kind of seen the process. In the last example, we saw the process for how we actually go through the mechanics of working with our equations. The problem here is we don't have any equations. So there's a step 0. Things we got to do before we do the calculus. And it comes down to just unraveling everything in this description. And it's going to be helpful to draw a diagram and then introduce variables. Probably use x's and y's, but if you want to use other variables, fine. All right, so let's kind of read through what is actually happening here. All right, so let's start. We want to plant a rectangular garden. Rectangle. That's a key word right there. So our garden's going to be rectangular. Let's draw it. I know how to draw a rectangle. Here we go. There's my garden. And we know with a rectangle, there's really 2 dimensions. There's the width and then the height. So we'll call those x's and y's. Maybe you call them w's and h's, or lengths and widths, or whatever you want to call them. Just be consistent. X's and y's is what I'm going to use. And we know for a rectangle, if this side has length y, then this side does as well. And then same thing for this other opposite side. That must have length x. All right, so we're drawing our diagram. We're introducing some variables. And there's a little bit more going on. So one side of this garden is going to be next to a house. All right, so let's draw in our house. So here's our house. All right, so we don't actually have to fence this side in because it's going to be right next to the house. And so what's going to happen is we're going to be putting a fence on the other 3 sides. All right, so conceivably, this side is going to be getting a fence, this side is going to be getting a fence, and then this other side is going to be getting a fence. So we have some fencing that's going in. All right, so we have fencing on 3 sides. And then that 4th side is against the house, so we don't have to fence that in. All right, so we've drawn our diagram. And we've introduced our variables x and y. Now we want to figure out, well, what are some of the different equations that we might be interested in when it comes to a rectangle. And so we see that we're dealing with fencing. And so we're interested in measuring, okay, what is kind of the perimeter here for this rectangle? So for a rectangle, there's different ways we can measure the size. We can talk about the area. So the area of a rectangle would be width times height, or length times width. In this case, if we use our variables, it would be x times y. Sometimes with a rectangle, we're interested in the perimeter. So this is where we, start at one point and then we figure out the lengths to get us back where we started. So we just kind of go around the rectangle and add up all the lengths. So, y plus x plus y plus x, it'd be 2x plus 2y. That would be the full perimeter. Now, for our problem here, though, is if we're kind of reading this over, we want to find the dimensions of the largest garden that can be enclosed using 40 feet of fencing. So if we're fencing in those three sides, those are the only three sides that we're worried about. So we're not actually worried about the entire perimeter because there's this one missing side. So we have this kind of extra, or in this case, this slightly varied calculation. Not entirely the perimeter. We're kind of looking at the perimeter of the three sides that we actually are interested in. So we'll call this the amount of fencing. Related to perimeter, but without that side we don't need. So let's go through and see how much fencing we would actually need. Well, we would need y amount of fencing over here. We would need x amount of fencing over here. And then we would need another y amount of fencing here. So it would be y plus x plus y. And if we add those, simplify that up, it'd be x plus 2y. All right, so, for a rectangle, there's the area, there's the perimeter, and then for this problem, what we're actually interested in is how much fencing are we going to need. So it's not quite the perimeter, but it's similar. All right, so, maybe there's other things we need to consider, but if we're thinking about the problem here, what is the largest garden? Well, if we're planning a garden, what we're worried about is how much space do I have in here to start filling up with some plants? I'm worried about the space. I want to have as much space as possible to put in as many plants as possible, while kind of keeping my fencing to this specific amount. So if I'm measuring the size of my garden, I'm really interested in maximizing the area. We'll bring that up again in a second. But just to kind of take a step back before we jump into all the calculus and everything, what are some different possibilities here? So what are some other possibilities here? Well, I might have like a really thin garden. Maybe that's would work. So maybe I have like this little really thin garden here where the width is 4 feet. And then I have 32 feet. So it's this really thin little garden here. And maybe that works out. What would my area be in this case? It would be 4 times 32. It'd be, 128 square feet. Okay, maybe that works out. But if I maybe make this a little bit kind of, more squarish, what else could I do? Well, I could have something like this, or maybe I have 15, 15, and 10. What would be the area of this garden? So if you notice, the area here would be 150 square feet. But if you're keeping track, this first configuration takes 40 feet of fencing. The second one here, 15 plus 15 plus 10, takes 40 feet of fencing. Maybe one more. Maybe something that's like 12 feet by 16 feet. So this would also take 40 feet of fencing. 12 plus 12 is 24, plus 16 is 40. So this would also take 40 feet of fencing. And my area here would be, 192 square feet. So you can see, with 40 feet of fencing, I can get these different rectangular shapes that have different areas. So conceivably, there's one configuration. If I could just get this just right, there's one configuration that would give me the largest size for my garden. And that's what we're trying to find. So we're trying to find the dimensions that give us the largest garden. And so just some different options here, but we're going to use calculus to help us find this. So that's step 0, just to kind of get a picture of what's going on. All right, now we kind of go through the general technique that we're going to use for a lot of these. So step 1, we have our potential equations that we might be interested in here. Now we just go through and identify which one's the objective, which one's and set up the constraint. So again, the objective equation is what we want to maximize or minimize. So we want to find, what is it? The dimensions of the largest garden. And so if we're thinking of maximizing or minimizing, we have some options here. We could maximize the area, maximize the perimeter, maximize the amount of fencing. But the amount of fencing and kind of related to that, the perimeter, we're kind of stuck with that because we're limiting ourselves to just using 40 feet of fencing. So that's kind of putting some restriction on how big our rectangle, on the size of our rectangle here in some way. So for the purposes of actually making a garden here, what we're interested in is we're interested in the space enclosed by this fence. That's the area. So what we want to do is we want to maximize the area. So that's our objective. We want to maximize the area. So we'll call that, just shorten that up to A. A is equal to X times Y. And that's what we're seeing here. How we measure our size of a garden generally would be the area of the rectangle. All right, so what's the constraint? Well, the constraint then comes down to how much fencing we have to work with. We only have 40 feet of fencing. So that kind of limits us. That puts some restriction, puts some constraint onto what we can do. So we're in some way limited by this. And so that's going to be our constraint equation. So we said the amount of fencing was x plus 2y. Well, we want that equal to 40. So x plus 2y is going to be equal to 40. This is the amount of fencing we're going to use. So it's kind of like the sort of the perimeter of 3 of the sides, and we want that equal to 40. All right, so we have our 2 equations. Now it becomes a little bit more routine. So we want to solve our constraint equation for either x or y. Either one's fine. This actually, I think x is a little bit easier to solve for. So let's solve for x. And when I do that, I get x is equal to 40 minus 2y. If I solve for y, perfectly fine, but then I'd have to divide by 2, and then I might have a little fraction in there. So this way I kind of avoid having to use any fractions, at least right now. And then once we've done this, we're going to take this result and plug it into our objective. So we have a is equal to x times y, and if I plug in x is equal to 40 minus 2y, I get the area now just in terms of y. So 40 minus 2y times y. And this is fine. We know we're going to be doing some derivatives, so let's multiply this out so we don't have to use product rule. So what do we get? We get 40y minus 2y squared. All right, so now we have this nice one variable function here, and now we're ready to break out the calculus. So that's step 4. Let's optimize this function. We know how to do it. So our function, we'll call it the a function, a of y, so the area function. And what was it? It was 40y minus 2y squared. And how do we optimize a function? Well, find the critical numbers and then classify the critical numbers, test them. So let's start. Critical numbers means we need to calculate the derivative. So we're going to calculate a prime. And when we do that, we get 40 minus 4y. And then we want to look, where is our derivative 0? Where is our derivative undefined? So if I set my derivative equal to 0, what do I get? I get 40 minus 4y is equal to 0, which tells me y could be 10. I also want to look at where the derivative is undefined, but that only happens if I have division by 0, and this is just a polynomial. I don't see any division. There's no log functions, no square root functions, nothing that usually gives me some kind of trouble. So this derivative is, well, actually I'm looking over here. This derivative also is a polynomial, also always defined. So no problem here in terms of an undefined derivative. So what we found is that y equals 10 is the only potential critical number. We just want to make sure, is it actually a critical number? And yeah, it is. So is this in the domain of our function? Yes. If we look at our function here, this is a polynomial. I could plug 10 all into this all I want, and I would get a meaningful number out. So yes, this is in the domain. So it actually is a critical number. So that means if I'm going to have a max or a min, this is the only spot where I could have it for this function. All right, so we've identified that we do potentially have a max or a min. Now we actually need to figure out, is it going to be a max, or is it going to be a min, or could it be neither? So this is where we have to classify it. And since these functions are so easy, probably second derivative test again. So let's calculate a double prime. What do we get? Derivative of 40 is 0. Derivative of negative 4y is negative 4. And if we're going to use our second derivative test, what we want to do is we want to plug our critical number, which was y equal to 10, plug it into the second derivative. We get negative 4. Negative 4, we're not too interested in the actual number, just the sign of the number. And in this case, it's negative. So negative means concave down. Draw in the concave down shape just to help remember what the second derivative test actually says. And so what this is actually telling us by the second derivative test if we draw in the shape, it looks like we have a max. That's what we actually have. So we have a local max at y equals 10. And since it was the only critical number, not only is that the local max, it's the absolute max. Kind of a bonus there. So only one critical number on the interval. Now what is our interval here? Well, technically speaking, this function is defined for all y. But realistically here, because we're actually dealing with a physical, we're building something physical that's going to exist in the real world, and we're talking about lengths and widths, we're not going to be dealing with negative lengths and negative widths, or even zero length or zero width. So our interval here might be the interval from 0 to infinity. Because we're actually talking about positive lengths. And we found only one critical number, not y equals 1, y equals 10. So it's the absolute max. This is as large as our function's ever going to get. All right, so that just about does it. Last step then is just make sure we answer the question. So use units if we need to use units, and let's just go back and make sure we're finding what the problem is asking us to find. So if we read, it's telling us find the dimensions. So find the length and the width of our rectangle. That's what we're really after here. And so we already found one of them. Y was equal to 10. And we can use our constraint then to figure out x. So in this case, we can use the constraint to find x. So what was our constraint equation? I forgot. What was it? This one right here. Actually, we already solved for it. Let's go here. X is equal to 40 minus 2y. So let's use that version. We already solved for the other variable. So go back to there, and let's plug what y is. So we get x is equal to 40 minus 2 times 10. Do the calculation there. We get x is equal to 20. And our units in this case are feet. So make sure we're using units. So we found our two dimensions. 10 feet, a 10-foot by 20-foot garden is going to give us the largest area. And that makes sense. If we go back to our diagram, we found x was 20 feet and y was 10 feet. So it makes sense because why x would be larger, because this one side we're not going to have to use a fence on. So it seems plausible that x would be 20 and y would be 10. Y we have to kind of fence in both of these sides. X we only have to fence in that one side. So it makes sense that the side we kind of get this benefit from by going up alongside the house, that's going to be the longer side. All right, so there it is, a nice optimization problem. We're going to try another one, but this is the general strategy. We're seeing how this works, and a lot of the work is just getting the problem set up. We don't actually get to the calculus until kind of this last few steps here. But in any case, we'll try another example next.